All right, looks like we're recording. So welcome all to the third and last for this semester data analysis seminar workshop. This one focused on mediation, moderation, obviously powerful statistical techniques. They're going to help us understand some of the more complex and nuanced relationships between various variables of interest. And by the end of the session, I'm hoping that you'll have a pretty solid understanding of when and how to use these methods in your own research. So we're going to cover a number of key topics. We're going to go through moderation first and then jump to mediation. If there's time at the end, I'd like to show how to do power analysis in GPAR. I doubt we're going to have time, so I'm going to just record that part separately, most likely, and put it in at the end in the recorded video. But we're going to do conceptual foundations for each of them to start one at a time. And then we'll dive into the two types of each effect, statistical methods for testing them, some proper data preparation, key assumptions to satisfy. We'll also talk about some of the common pitfalls that folks run into. And then we'll walk through practical examples, the same data we've been working with through the semester. And I'll introduce you to running these in both SPSS using the process macro and in RStudio. And we're going to run those side by side this time. So with previous seminars, I'm sort of assuming that you've watched some of the other videos or otherwise are familiar with these methods broadly, that you've already downloaded the GitHub repository, especially if you want to follow along. I've made some changes up till the last, hour and a half, minor changes to it. So I'll put the link and the zip file there in the chat for folks, so you can download it there if you want to follow along. Again, we're going to move at a pretty quick pace, so I'm not going to stop for questions, but if questions come up, just interrupt me, please, because I think it would be valuable to answer them and walk through them. Yeah, re-download that or use the new repository if you want to, in the chat if you want to follow along. Okay. As before, this will be recorded and on YouTube. It'll have chapters, so you can jump to the chapters that you need or want. Okay, so like I said, we'll start with moderation. So what is a moderator? What is moderation? It's a variable that affects the strength or the direction of a relationship between a predictor and an outcome. Essentially, it's answering some key questions framed as when, for whom, or under what conditions does X predict Y. So for example, you can think of this sort of moderation model here, the relation between stress and depression, depending on level of social support. So maybe for those with high social support, stress could have a minimal impact on depression, while if you have very low social support, stress might significantly increase depression. So you'll notice in the diagram, the moderator, sometimes you'll see this as W, sometimes you'll see it as Z. This is, this arrow is drawn to intersect with the arrow between X and Y. This is how you'll see moderation shown in figures. This is typically tested statistically using an interaction term or multiple interaction terms, depending on how complex your moderation is. We're just going to be doing two-way moderation in this example. And the way you get an interaction term, pretty simple. It's multiplication. So you're just multiplying the predictor by the moderator here. Okay, so two types. Doesn't affect how you model them, but this is often what you'll see, these different types of moderation. So first is the moderation of the strength of the relationship of X to Y. And so what you'll see on the left side here is called an interaction plot. This is a figure that should always be included in any manuscript or poster that uses moderation. Moderation can get pretty complicated to think through. So, we definitely want to have this visual to help folks, including ourselves, understand what we're finding, what we're talking about. So when we have moderation of the strength of a relationship, the interaction plot will look something like this, where the slopes will vary in their steepness, but they all go in the same direction. So This is using that previous example, social support moderating the relation between stress and depression. You'll see the interpretation for this effect here in the lower right that you might include in a poster, an abstract. So social support, let's say this was a significant finding. It significantly moderates the link between stress and depression such that higher levels of social support attenuates or weakens the link between stress and depression. So visually interpreting the interaction plot, we can see, when stress is low, the level of social support only marginally influences depression. It's sort of in that normal to mild depression range on the PHQ-9 here. But when stress levels are very high, the influence of social support on depression is much more pronounced. So that's some of the ways you might visually interpret our moderation relationship when it's the moderation of the strength between these relationships of stress and depression. Next up is the moderation of the direction of a relationship. It's pretty self-explanatory when you see the interaction plot. Here the slopes vary, but now we see that some slopes are positive. Well, one is obviously positive, one is kind of slightly positive, and the other one is negative. And so this is this moderation effect is pulled from the literature. It's a real example of where we find this type of moderation. And it's the influence of social support on the relations between work stress and job performance. So I think some of these, excuse me, these like moderations of the directions of a relationship are often most fascinating and most interesting to get into. Not that the strength is any less valuable, but this can be kind of like, oh, wow, very surprising. So again, in the lower right, you'll see the interpretation. It's a little bit longer this time. So social support moderates the link between work stress and job performance such that for those with high social support, higher levels of work stress predicted improved job performance. Conversely, for those with low social support, increased work stress predicts decreased job performance. So you may notice that in both of these interpretations that we've gone through, well, we're going to include this additional information contextualizing the moderation effect after using the word such that. This is really important. You have to characterize the moderation effect fully for it to really be meaningful for readers. So when you report these type of results in manuscripts where you have more space to write, I recommend plugging in, like using the regression equation and plugging in the extreme values of your predictor that you're finding in the sample population. Because a lot of times the graphs statistical software will generate don't actually consider what is a realistic score. It might show you an interaction for someone who's like, negative 30 on the PHQ-9, a score that's not attainable actually on the scale. So I recommend where you have more space, plug those in. I'm going to show you an example of that later on, and then write out what you find through that process in a narrative form, like make it about a student or about a participant in particular, and under what conditions, the predictor, the moderator influences the relation between, like, let's say, work stress and job performance. So as I mentioned before, how do we test it statistically? It's pretty simple. Here you'll see in the moderation beta 3 coefficient, we're just multiplying these two, the predictor and the moderator. And you include that in your regression equation. So I put the equations here, replacing the words for our examples, so you can get an idea of what the equation would look like for this sort of plugging in that we'll do later on. So if you have a statistically significant interaction effect, that's a beta 3, that would indicate the relationship between your predictor and outcome significantly depends on the level or the value of your moderator. So the equation here includes our predictor, moderator, the interaction, and again, finding that, if you find significant moderation, you're going to conduct a simple slopes analysis to interpret that effect. Like I said, looking at it, plugging in different levels of the moderator, what happens to the relationship between X and Y. Typically, we'll look at one standard deviation above and below the mean, as well as the mean, or all categories, if it's categorical, nominal variable. So as you can see, these are, incredibly helpful for visualizing the effect. If you just looked at the equation, it doesn't really make a lot of sense. So as I said, significant beta 3 is going to indicate significant moderation. We're going to do that simple slopes analysis to help with our interpretation, and always visualize using the interaction plots. So for data preparation, which we'll go through, you're going to want to mean center all of your predictors. It's a key step in moderation. This is just subtracting the mean value from each observation. It can get kind of tricky when you're plugging in values, into the equation. So just a really quick example here, if our mean was 3.5 on the PHQ-9, then 0 would be that 3.5. A -1 on the mean centered value would be 2.5. +1, 4.5. So that's all that mean centering is doing. It doesn't affect the values of the coefficients, but it will affect your intercept. And that'll make a lot more sense as we go into the examples of plugging in. Now, we also want to properly code categorical moderators. So when it comes to reciprocal categories, dummy coding is okay. I prefer effects coding either way, but dummy coding works. So when you let's say if you have a dichotomized gender, male, female, that's like every person that answered, male to one item has a 1 and a 0 if they're not male, and then the female category would be the exact opposite. So that's a reciprocal category. Then non-reciprocal is going to be when you have multiple categories, where you're just going to code them as -1, 0, and 1. Some additional assumptions for moderation. This, all of the multiple linear regression assumptions we covered in the second data analysis seminar apply, including known multicollinearity, which we test with the variable inflation factor you'll see in the code. But if you are using SEM, software to test for moderation, if you're using maximum likelihood estimation, then you need to ensure you have multivariate normality. Generally, if you fail this, you can go and use MLR, which is maximum likelihood with robust standard errors. Nowadays, the best practice is considered just to avoid using maximum likelihood estimation altogether and just to use MLR instead, as it produces less biased results. And the more complex your model, the harder it is to satisfy this multivariate normality assumption. Next up, common pitfalls. So first one is interpreting the main effects without considering significant interaction. So if you have a significant beta-3 significant interaction, that influences obviously how X predicts Y. So you can't just go in and interpret the simple coefficient for the predictor on the outcome without considering, those main effects have to be considered in the context of the significant moderation. Now, not probing for significant interactions, that's something that some folks will do, not understanding them in their full context. So looking again at the simple slopes, really understanding the nuances of this moderation effect in the context of your sample itself. And we'll go through that in detail. Of course, the easiest way to probe an interaction effect is to visualize the effects as we've seen. And without that visual interpretation, it's really difficult for both us and readers to understand. Another one is mistaking statistical significance for practical significance. So we can find significant moderation, but it may have a really small effect size. Again, plugging in the extreme values in your actual data set and your sample can help a ton with this, to be like, oh wow, the slopes look really different, but really the effect is quite small. And then lastly, we're going to do a two-way interaction, but you can do a 3, 4, 5-way interaction if you want. The more interaction terms you add in the model, the more overfitting you're going to have. It's going to lead to false positives. And so you should make sure you have a really clear theoretical justification for each interaction that you're testing. And that involves, as always, a really thoughtful, in-depth review of the literature, what others have investigated and found, in addition to what you're thinking about why the moderator should influence how X predicts Y. So we're going to jump into the moderation example here in R. I have the code for a nominal predictor and a nominal moderator, continuous predictor and a nominal moderator, and continuous for both the predictor and the moderator. We're going to go through the first two during this seminar. The code is there for the last one, but the middle one here, continuous predictor, nominal moderator, gets kind of the trickiest to interpret. So we're going to use that example to work through plugging in and understanding what all the coefficients mean. And we're also going to do this, like I said, side by side with the SPSS syntax file called moderation syntax, and we'll go from there. So I'm going to jump out of this slideshow here, and first thing I'm going to do is add the pictures of the of those two slides I just showed into the chat. So if you want to reference those, the line numbers, you can open those up and look at them. But we'll start here with our number 2 file, moderation.r. And again, interrupt me if you have any questions that are coming alive for you. So we already did in the data cleaning, and we use it again in the data analysis 2 seminar. We already created the script to clean our data. So as promised, we don't have to go through all that. And this is where in R, we can just use the source function and type in the path to our data cleaning R file and just run this single line of code. And what that's going to do is run the entire data cleaning file for us. And as before, you'll see it'll pop up with everything we've done, including that close to APA 7 formatted demographics table. So again, another one of the benefits of doing all this coding and keeping it all is that you don't have to redo that work. That's just done. So again, I'm not going to go through all of this code line by line because this is all covered in the other seminars, but I will describe what it's doing. So here we are selecting the variables of interest, and we're going to remove in the sample data, there's one participant who endorsed another gender other than male or female. So we're going to remove them just for the sake of this example. Obviously, we don't have the statistical power to investigate them as their own group, just n equals 1. So for this example, we're just going to get rid of that single participant. And then we're going to look at the data structure to make sure everything looks right. Should all be numeric, and it does. So the variables we have here, PHQ-9 items, audit items, flourishing scale, Diener's flourishing scale items, past month outcall use, GPA, and the reciprocal gender male, gender female categories, 0, 1. Similarly, we're computing the 2 totals and the 1 mean. So total audit score, total PHQ-9 score, and the total flourishing score. We're going to look at those histograms, descriptives as well in this block of code, but this is making sure that we're only including in the sums or the means folks who answered all the questions. So if they skipped an item, they get an NA for the total. We don't want to bias that score. So we're only using the complete cases to calculate our totals. We'll do our missing data analysis based off of that. So we'll generate the histograms later on, but you'll see down here in the lower right, we have our histograms and our descriptives popping up in our console. Now, this is an important step we didn't cover before, but when you get into some analysis, you're calculating total scores and whatnot, it's a good idea. You'll need it later just to store this in your R environment as a backup. So I'm just turning data backup into what our data is right now. And now my backup will have all of my single items, and I'm going to just select my totals in a new data set, replacing it with data. So if I look at these, you see data backup has all of those item columns that we don't actually need for our analysis, and data is a much simpler, more straightforward data frame that has just what we're going to be using. So I wanted to go through the missing data, even though we went through the basic principles in the second seminar. I think it's worth going into the step-by-step here because it can get nuanced. How do you actually do this when there's more complex missingness? So the first step, I'm going to look at my missing plot and see the light blue. So we have a lot of missing audit scores. And there's some folks that are missing quite a bit. If I look at the missing pattern, we'll get some important information here. We see that we have 54 cases that are missing nothing. We have 27 that have audit scores, have all of these scores together, but we're missing from 44 are missing any audit total. So this is where this is the important column here to focus on for missing data analysis, because this is going to be our first target. We're going to go one by one through the missing data. Fortunately, we won't have to go through all the steps. You'll see why. But this is our target. We say, okay, we need to examine if our missingness is completely at random. If it is, we can just omit the missing rows and move on. Or we could use multiple imputation as well. But if we run our MCAR test, we see unfortunately, we have significant findings. That's going to tell us that we have to reject the null hypothesis that our data missingness is MCAR. So there's some other mechanism going on. So as you saw in the second seminar, we're going to have to figure out, does anything predict the missingness in our data? And this is where starting with the most missingness is important to know. So we're going to first try to predict missingness in the audit total. We do that by making a 0-1 variable that is called missing audit total. So when this new variable is 1, that's where audit is missing. When it's 0, we have the audit score. So to make that variable, I'm going to assign it as an integer, 0-1. And then importantly here, we're going to try to predict it using logistic regression. So what you do is you set the missing audit total, that new variable, 0-1, as the outcome. And we use all the remaining variables in our data set to predict it using binomial regression here, logistic regression. So when I run this, we're hoping that one of our variables is a significant predictor of missingness in audit, and lo and behold, we have one. Past month outcall use. Now, if you know the intricacies of our surveys, you know that this makes a lot of sense. Why outcall use in the past month predicts missingness in audit. If you say you don't use outcall, you're never presented with the audit in our survey. So this coefficient here, which is a log odds, does make sense. If we go through and we exponentiate our log odds to give us an odds ratio, which will be called OR here, we can see our odds ratio is 0.607, 608. When an odds ratio is below 1, it means that the odds are less than 1, so lower odds of missingness. So one way I could say, that for each increased day of outcall use in the past month, the odds are 0.6 that they'll be missing audit, or I can subtract 1. I can subtract the odds ratio from 1 to get a more reasonable interpretation, which you'll see here. For every additional day in past outcall use, the odds of missing the audit total decrease by approximately 39.2324% actually. So we can now impute the audit total. A couple ways to do that in the mice package. I'm doing sort of the simplest way. Here's that data backup, why it's so important. We're going to roll back to our data backup with all of our key variables. And we're going to, in this case, the simple approach is just to impute all of the variables. So I'm going to go through and impute everything. If I looked at the final fit, let's see, this is now imputed data. I have to complete this. We should see now we have no missingness, but I don't want there to be no missingness. I only really wanted to impute the audit. So I can go through and use a for loop just to pull from the backup to restore the missingness. And so that's what we're doing here with the non-impute columns. So for each of these columns, I'm saying restore that column with the backup, which has all the missingness. So when I run that, you'll see our audit total has no missingness. and the missingness from our other variables is retained. And we'll see that again in our audit total in the missing patterns. So next step, let's run our missing completely at random again. So here we have it. We now identified that the missing at random data was constrained only to the audit total. So now that we've imputed that, use the proper methods, we no longer have some problematic missingness. We have missing completely at random, and we can either just omit or impute the rest of the data. In this case, I'm just going to omit that data. And lastly here, I'm going to write that clean data that the missingness has been handled to a CSV file in the data folder, which you'll find in the repository. And that's where we're going to, now that we've done all of this stuff, that's really much more advantageous to do in R. Some of the imputation you can do in SPSS, it's just a lot more complicated, it gets pretty messy without much ability to track what you've done unless you're saving your output. So this is why I like to do, work in R. It makes things a little bit harder. You have to understand what you're doing, and that's helpful to you as a researcher. So I'm not going to, go through and look at all of these in detail, but we're going to jump into SPSS and run these side by side. We'll go through the moderation for each. So what you're going to do is go into the SPSS syntax folder and open up the moderation syntax. It'll take a moment to load for me. And when you open this up, you're going to see the syntax file open up as well as a blank data set. So don't exit out of this. SPSS doesn't run if you don't have at least some type of data here. What we're going to do is we're going to go to File. We're going to import our data, CSV data. And here it is, data clean. SPSS is going to ask us some questions about the CSV. The way that R saves a CSV is default acceptable to SPSS, so you can just go ahead and hit OK. When you do that, you'll see your data is now, blank data set's now replaced with the imported data, and your output file will open up, and you're going to see what was done. Now, this isn't exactly what we wanted. There's no labels. There's nothing here. Also, we're going to be using an abstainer category, effects coded, in both SPSS and R, and so we don't have that category. So the first section, lines 1 through 22 of the syntax file, if I run these, you'll see it just populates with our labels. It gives us some values for our dichotomous. It makes sure that our measures that are scale are scale, the one that is nominal. Again, we reviewed this in the data cleaning workshop, so I'm not going to go through in depth what this is all doing, but you have the syntax and you have that video to reference. In R, we made our abstainer variable using an if-else statement. So if alcohol use was 0, make it a 1, otherwise it's a -1. That's effects coding. Here in SPSS, we're going to do the same sort of thing, except using 2 if statements after we instantiate the abstainer variable using the compute function. And then I'm going to add the levels, the labels, and whatnot, just as we did for the other variables. So what you'll see in SPSS, once you do that, is again, new variable is calculated, -1, 1, and the labels and everything are populated appropriately. So as we did in R, we're going to look at our descriptives in SPSS, our histograms. Nice thing about SPSS is that the histograms show a normal distribution over the data. There's a way to do it, but not in the base functions in R. So one of the things I do like about SPSS is it does that for you. So we have our histograms, we have our descriptives. These will all, of course, line up, 81 cases in our data set. So now I'm going to jump back into R as we did before. Again, you'll see there's no syntax for using process macro to do this analysis because it's all point and click. and it won't save all of the parameters. I mean, some of them will be saved in the output, but it won't save exactly what you clicked in all the settings. So we'll go through those after we run through the analysis in R and see what we're really needing to do step by step. So we have two nominal categories, two categorical variables rather, predicting depression, so abstaining from alcohol and gender male. And we don't have to do any mean centering because these are categorical. So what we're going to do is we're going to do a nested model test here. So I'm not going to go through the assumptions. Those are in the second workshop, but you're going to look at your restricted model. So we have no moderation, no interaction included here. And you can look at the summary. I generate the summary really because you're probably going to want to look at the plot to examine, do your regression diagnostics to make sure that you satisfied all the assumptions. So those aren't in here. There is a file, the assumptions, 0 assumptions of MLR, that you could go through and start to change the variables and go through and test all of these. But we're not going to do that in the interest of time, but you absolutely must. So we do our restricted model, no interaction term, and then we're going to do our full model, which includes, it's exactly like the restricted model, except we include our interaction term here. And our first step is to run an ANOVA on both of these models. This is asking and answering the research question, does the inclusion of our interaction term improve the model, explain any additional variability in depression scores compared to the restricted model? And here you'll see we have a non-significant finding, which is telling us this is not a good moderation interaction term to include. Doesn't actually explain a significant portion of variability more than the model without the interaction term. Nonetheless, we're going to go through the steps and look at the summary, confidence intervals, and the way that I set this up is you will see exactly in the same order what SPSS is going to show you. So I'm going to just generate all these. SPSS I don't think includes, process doesn't include the standardized coefficients, but the R code is here to include them. And then we're going to generate our interaction plot using the SJPlot package. And you'll see, great thing about R, the SJPlot package in R, is that it'll give you the confidence intervals. So in SPSS, you don't get those, but you can see here, even though the lines are pretty different, the confidence intervals are overlapping. So that's where you can really tell that this is non-significant moderation. As promised, we're going to jump into process. So if you haven't installed the process macro already, I am assuming that you have if you're following along, but I included the files in the repo, and you just have to follow the instructions for how to execute this, but it's just installed using a syntax file. Importantly, also is the process model templates in the repo, and you'll see why this is important to have access to, and it's surprisingly not that easy to find online. So definitely store this away somewhere on your computer if you're going to use process. So let's open it up. We go to Analyze, Regression, and if you've installed the process macro, you'll see this process version, whatever you have. Mine is 4.2 popping up. And you'll get this great little menu here to run your analysis. I'm going to switch these over to variable names so it's a little easier to read. I do that by right-clicking and clicking display variable names. And we're going to run the same model that we did in R. So we're going to have our PHQ-9 as our outcome, and we're going to have our abstainers as the moderator and our gender male as the X variable. Couple things you need to set here. First one, model number. So as you see here in the PDF, basic moderation is model 1. The other model that we're going to use is model 4, basic mediation. But let's say you wanted to run a model that looked sort of like this. You would want to select model 58 from this dropdown. So that's why it's important to have this as a reference so you know what model you're testing. So we're just using 1 and 4 today. You selected the correct model. We're going to come over first to long variable names. We're going to have to accept this warning, this risk of incorrect output, because our variable names are longer than 8 characters. The only time this is a problem is if you have multiple variables in your model that the first 8 characters of the variable name are identical. That's going to cause a big problem. We can accept this risk because we know that PHP9, gender male, abstainers, none of them, the first 8 characters in their names are not the same. So we can go ahead and accept this. If you don't click this checkbox, it will throw an error and not give you results. So you want to make sure you do that. Next up, we're going to go to the options. If through your testing the assumptions, you found that you violated the assumption of homoscedasticity, you may choose some robust regression criterion here to make sure that you're not having biased results. You have to, Huber White is quite common. I've seen folks use a number of them. There's certain types of violations of assumptions will help you guide you to which method you might want to choose. Today we're not going to do that, just for the example. Cool thing about the process macro is, we'll do mean centering manually in R, but process macro lets you mean center variables if they're continuous variables that define products. That's typically what we'll select, but again, no centering. These are 2 categoricals. Then we want to probe interactions that are where the p-value is less than 0.10. We want to generate some information about those. Then we're going to check a few check boxes here. We're going to look at the code for visualizing the interactions. And I believe, let me double check, I think that is all that we're going to test. So yeah, we're not going to include X by M interactions. That would be if we had a moderated mediation model. We would want to look at that. So you'll need to select that. So we're just going to generate the code for visualizing the interactions here. Hit continue, and then hit OK. And then things will start plugging away in your output. Might take a minute or 2, less than 10 seconds usually, and you'll see this output. Now this is going to be presented in some of the same order here. So all of these findings will be the same. We have our R squared. You'll see SPSS does not use the adjusted R squared, which is what we should be using. It just gives you the multiple R squared. So it's a disadvantage. But all the coefficients will be the same. Here, as you'll see, these are in a little bit of a different order. Gender male appears up top. Coefficients are all the same. You do get confidence intervals that should be the same. We get our ANOVA results down here, which we see non-significant improvement in model fit when we compare the model without the interaction term with the interaction term. So we see our interaction is non-significant. P-value is 0.543, and our confidence intervals cross 0. So we can be very confident this is not significant interaction. To generate that interaction plot in SPSS, we're going to you have to double click this to be able to select this. And then you just copy this code, this block here, and you go into your syntax file. I've already pasted this code, and you run this. And then our output will show, first it's going to generate a new data set here that shows you, various levels, the different combinations and the predicted PHQ-9. So it's using that to make your plot. Just going to get rid of that for now. And then look at our output. See, where is our output? Here we go. So our output looks like this compared to in R looking like this. So not as friendly. Of course, we can get the lines. You just double click the graph and you go up to this little icon here. If you hold your mouse over it, it'll say add interpolation line. That's going to give you your lines, but it's not showing you your confidence intervals. So again, if you weren't looking closely at the PHQ-9, the y-axis here, you might think, wait, what do you mean? This looks pretty different. These slopes are at least a little bit different. Intercepts are certainly different, but it's much clearer in R where you see, yeah, there's definitely no significant interaction. Any questions about this before we jump into the next one? The next one is the one where we're going to really dive into the coefficients and interpreting them.
I don't have any questions yet.
Okay. Gotcha. All right, let's jump into it again. Interrupt me if you have questions as we go. I'm going to exit out of this output and move down to line 246, continuous, predictor, nominal, moderator. So here, like I said before, we're going to mean center our continuous predictor. We're going to use psychological flourishing. And I'm going to just make sure that that's numeric after I mean center it. We're going to go through the same process. Now that we have a continuous predictor, I'm going to look at the variable inflation factor to make sure there isn't any multicollinearity. Of course, it's not going to be that valuable because we have a nominal predictor, but it does give us some information about whether we have some problems in the association between scores of the Diener mean and the by gender. So similarly, we did the restricted model, Diener mean centered by plus gender male, and then the full model, we just include those two in parentheses multiplied. And we can look at the variable inflation and see that it goes up. We have an interaction term, so the variable inflation will go up. More multicollinearity, but it's below 5. That's the cutoff. Ideally, below 5, certainly below 10. So we definitely don't have any significant multicollinearity here. And now we're going to pull up the summaries of the full model. Let me open this up so it displays a little cleaner. Confidence intervals, the ANOVA, and our beta. So first step, we're going to look at the ANOVA. Looks like we do have a significant improvement in model fit when we include the interaction term. So that's going to give us license to look at our full model's output, which shows we do have significant interaction. And if we go through and plot our interaction, we see, given the confidence intervals, that we do, in fact, have some pretty different slopes here. Lastly, in R, we're going to use the simple slopes in the EM means package to show us what our slopes are. Let me open this up a little so we can take a look at those a little clearer. Shows us what the slopes for Diener mean look like for each group. I'm going to go through and open up all the same findings in the order that we would see them. Generally, it's going to be the summary, then the ANOVA. Actually, it's going to be summary and confidence intervals, ANOVA, this, and then the simple slopes. So this is kind of the order that the process macro will show us. Again, jumping back over to SPSS. Same place, regression, process. This time we're going to swap out Diener mean for our predictor and gender male for our moderator. We're going to keep model 1. Since we haven't closed SPSS, everything should be retained here, but again, we want to make sure that we center our continuous variable, Diener mean, psychological flourishing. The rest can stay the same. So now we're centering that, and we're going to run the analysis, and we should see in our output the same findings that we have in R. So we do see we have the significant interaction term, not crossing 0, confidence intervals, p-value is 0.0074. Similarly, significant improvement by adding in the model fit when we add that interaction term. So it's going to give us likeness to investigate this. We see our conditional effects that will look exactly the same as what we see in R for the simple slopes analysis. And this is why, like I said, you have to interpret the results in the context of the moderation, because we see that if we just look at our main effect, we see that we have a significant effect of flourishing on depression. right? But we can't say that that's the case for both men and women, because when we look at our conditional effects, what we'll see is that it is for women in our sample significant, but non-significant for men, which is or corresponds to this very shallow slope that we see here in the interaction plot. Similarly, we can show our, it's going to be this one, we can show our interaction plot in SPSS. It's going to make that new data set. Go ahead and exit out of that and look at our output. Here we see the same type of interaction plot and add our trend lines. And what you'll notice here, which is what I don't like about the interaction plot in SPSS with the process macro, is that we're limited. It's only showing 1 unit below the mean up to 1 point something, 2, 3 or so above the mean. Whereas in the SJ plot package, it will show you the interaction plot for the full range of scores in your sample. So if I were to open up data and look at the Diener mean centered, we'll see we have our lowest scores are more than 4 points below the mean of Diener mean. I'll show you that here by just sorting that. So we have a negative 4.32. So the interaction plot in R is going to show you the full range. So that's one of the reasons I really like using the SJ plot package. So our results. I'm going to go through and show you with this example, plug them in and show you how to interpret them. I'm going to switch over to our PowerPoint again and go through these. So here's our regression equation with the betas just marked as betas. And if I start to plug in what we found number-wise, you'll see that the intercept is 9.61. Our beta 1 was negative 3.45. Our coefficient for gender male was negative 3.16. Our interaction was about 2.80 positive. So how do we interpret all these coefficients? Let's first start with the intercept. So we're going to use this, our hint table here to help us with these interpretations. So how do we get depression to equal 9.61? Well, we have to get rid of everything else in the equation, which means we have to zero these out. All these should be multiplied by 0. How do we do that? We use the mean of flourishing and female for the gender. So this is 9.61 is the predicted depression score for females whose flourishing score are at the mean. This is one of the reasons we mean center, in addition to avoiding multicollinearity, is it helps make our coefficients a little bit more meaningful. If we didn't mean center flourishing, this would be the predicted score for a female whose mean on the flourishing scale was 0. That is not an attainable score on the flourishing scale. The means range from 1 to 8. And in our sample, they actually range from 1 to 7. So that's what this first coefficient means. And we're going to skip one. We're going to go to the gender male coefficient. Again, this is 0 is female, the reference group, and 1 is male. So you got to make sure you really know which is which here. This is the predicted, the difference in predicted depression scores between males and females in the sample at the mean flourishing. So that's negative 3.16. So what does that really offer us? Well, it gives us the ability to calculate the intercept for males, right? So this is the females, and this is the difference between males and females. So if we add these two numbers together, 9.61 plus negative 3.16, or minus 3.16, we get 6.45, and that's our predicted intercept for males in our sample. So that's how you can sort of use the intercept in the gender male category to obtain the intercept for males. Another way to do this, you could just run your analysis again and swap out the reciprocal category, and you'll see these two coefficients change. But many of the coefficients will change, but the interpretation will be the same if you calculate it out. And then we're going to do the next two coefficients. The first one is the beta 1, the coefficient for flourishing. This is telling us the predicted change in females' depression for every 1 unit increase in flourishing, right? So this is our slope for females, right? And our interaction term is telling us the difference in predicted depression scores between males and females for each 1 unit increase in flourishing. So just the same as we did for the intercepts, we can use these two numbers to obtain that missing value that we don't have from the equation, which is what is the slope for males? Same deal. Take our negative 3.45, we add positive 2.8 to it, and we get negative 0.65. Fortunately, you don't have to do this math on your own. You may recall, you'll see in our simple slopes analysis, that's taken care of for us, as well as the significance testing for it. So plugging these in, I went through, this is our cheat sheet. You know, this is kind of important to have in your mind or somewhere as you plug in the values. Want to know what's the percentage. So we have mostly females compared to males. It's not super imbalanced, but I'm going to, as a result, be more confident in the results for females than I am for males because I have more of them in my sample. So I think that for females, this slope will probably generalize better, slightly better than for males. Also, we want to know what our range is of the flourishing scale itself and in our sample, what our mean and standard deviation were. Same deal for depression. It ranges from 0 to 27. We only had 0 to 22 in our sample, the mean and standard deviation. So what do we do with that? We start to plug in our sample minimums, mean minus 1 standard deviation, our mean plus 1 standard deviation, and our sample maximum. These numbers may look kind of funky. That's because we're putting in the mean-centered values. So the mean of flourishing was 5.32, and our minimum was 1. So what's 1 minus 5.32? Negative 4.32. So this is just for males because we have the 1 here. And so you would do, you know, this is 5 equations. So you'd run the equation 10 times, and you'd get a table that looks something like this. Flourishing level minimum, standard deviation below the mean, mean, 1 above the mean, and the maximum. I put here the mean centered and the original value of the scale to help get an idea of where we're getting these numbers from. And then we look at our predicted depression and for men and for women in our sample. And we'll see the trend as we go from the minimum to the maximum of flourishing. Depression goes down slightly for men, but for women, that is a much more pronounced effect. And so this could be used to show that, to basically plot out manually that interaction plot. So that's it for the moderation. I think we're right on time. The slides and the moderation took just about an hour. Any questions about moderation before we jump into the next stat for mediation?
I don't have any questions.
Okay. And as before I mentioned, you can always reference the video when we get that uploaded. Okay, now we're jumping into mediation. So mediation answers some different key questions. So this is, you know, how a variable affects, how X affects Y, or the mechanism through which X affects Y. So, you know, when a predictor affects the outcome either partially or fully through this third variable, the mediator, we're looking at mediation. So here, we're going to look at a few different effects, looking at this example of social media use influencing academic performance. So we have our C prime, which is our direct effect of social media use on academic performance, our A path, which is social media use's influence on sleep quality, and our B, path, sleep quality's influence on academic performance, and then our total effect, which is just the addition of our direct and indirect effects. And so when you're reporting mediation, this is generally what the figure will look like, except you'll have your standardized coefficients here. And you may report your direct, indirect, and total effects in a table, for instance. But this is the location where you'll see the coefficients displayed in a figure reporting mediation. So what is full mediation? Full mediation is the indirect effect A times B is significant, and the C prime, the direct effect, is non-significant when we add our mediator. So what that's telling us is that the entirety of social media's influence on academic performance is occurring through sleep quality and not directly. And then conversely, if we have partial mediation, same deal, significant indirect effect, but the C prime stays significant when the mediator is added. So only part of the influence of social media on academic performance occurs through sleep quality. So this could happen for a number of reasons. Of course, one of the things to think about when you have partial mediation is omitted variables that could be explaining this. Maybe there's a moderator here, or maybe there's some other variable. This is sequential mediation where sleep quality then affects something else before affecting academic performance. So you want to ask that question when you have partial mediation. Is there something that could be relevant here theoretically in the literature through your literature reviews that could influence this? Statistical methods, I'm not going to go through Barron and Kenny's causal steps from 1986. They're sort of outdated these days. So Bell's test you'll still see being used, sometimes, but sort of negative aspect of so Bell's test is it does follow a normal distribution. It requires a normal distribution, which is often violated when you're multiplying two coefficients. And we'll take a look at some of that in R. So modern approaches, we want to use bootstrapping, bootstrapped sampling for estimating the confidence intervals for indirect effects, which means we're not relying on p-values for our indirect or total effects. So you can use the process macro, this is where I think the process macro really shines, is for mediation. And we're going to use structural equation modeling using the Levon package in RStudio to go through these. Critical assumptions. With mediation, a new assumption comes in that we're going to violate this one in our example here, but we want to see temporal precedence. So in a perfect world, our predictor, the data collection for our predictor should come before we collected data for our mediator, which should be collected before our outcome. So that's preserving perfect temporal precedence. First, the predictor happens, it influences the mediator next, which then influences the outcome. 3 time points minimum is really the most ideal situation for mediation. Justifies mediation as an analysis approach. At the very least, the predictor should precede both the mediator and the outcome in time, or the other way around, the predictor and the mediator should precede the outcome in time. So at least we should have some type of reference for temporal precedence. And depending on the variables you're using, there may be theoretically grounded reasons why you don't need 3 time points, but obviously 3 time points collected thoughtfully at thoughtful times that would correspond to what you expect. In an experimental design, like an intervention, that would be critical for temporal precedence. Similarly, we don't want any multicollinearity. We're going to mean center variables for that reason as well. It does help to prevent suppression effects. We're going to talk a bit about suppression because it came up in this example, so it's worth going through the steps. Same, no influential outliers. This is in the MLR assumptions, but something that can definitely influence the bootstrapped coefficients a bit more than when you're just doing other types of analyses. So something to really tune into. And then having adequate power is across the board, something that we want to make sure we check in advance of running analyses. but again, really important for bootstrapping, as well as, if you have a small sample size, certain methods are really not going to be reliable. Common pitfalls, you'll see this in the literature. This first one, folks doing mediation with cross-sectional data, you're failing temporal precedence. It's really not an appropriate method for cross-sectional data, and we're going to violate this one big time during the example. I already talked about omitted variable bias. You might fail to include an important variable that could explain the relationship between social media use and decreased academic performance more than sleep quality. Maybe it affects stress and anxiety first, and then affects sleep, which then affects sleep quality, which then affects academic performance. So that might have gotten rid of that partial mediation and turned it into full mediation, for instance. Reverse causality, again, why you want to have temporal precedence. You have to sort of think, it's all one time point. Why isn't Y causing X? Why is it X causing Y? And so this can be kind of tricky if you're using cross-sectional data, but something to consider. Grounding it in theory, why is the direction the way you're saying it is? Confounding the mediator outcome relationship. I've talked about this a little bit already. You can get some spurious effects. So if a confounder is influencing both the mediator and the outcome, right? If that stress and anxiety is influencing both academic performance and sleep quality, then you should either include it maybe as serial mediation or at least as a covariate to control for in your analysis. Failing to investigate suppression. So if you have a suppression effect in your model and you don't investigate whether it's problematic or not, that's a major pitfall, because that can just be an artifact of multicollinearity, biasing your results. So you want to make sure you investigate that if you have it. Same as any other analysis, ignoring measurement error is going to be a big problem. And then lastly, using p-values to infer statistical significance for your indirect effect. P-values rely on a normal distribution, and generally bootstrapped results do not follow a normal distribution. Very, very rarely do they. So that's a big problem. A little bit more about that. Why not p-values in mediation? As I said, you're multiplying two coefficients, A times B. And this is going to be rarely is it going to be normally distributed. So p-values assume normality and assume a large sample size. We often violate those assumptions, so our inferences could be biased. So we use bootstrapped confidence intervals instead. Bootstrapping takes your sample size, we have 100, takes your sample size and we do 5,000 bootstrap samples. It's going to go and make 5,000 new data sets with replacement. So you could have 2 of the same cases in that data set, or 3 or 4. And it's going to run your analysis on each of those data sets and then take that distribution of results and calculate confidence intervals. Lavon uses the delta method. This is where Lavon is not great for mediation. By default, it'll rely on normality assumptions. So we're going to use the SEM helping hands package to get those non-parametric bootstrapped results, confidence intervals, which is the default in the process macro. But we'll show you that side by side here. So p-value, when you're looking at your indirect effect, might suggest that it's non-significant, but we're not trusting those p-values at all. The assumptions are violated. We're going to look at the bootstrapped confidence intervals, and if they do not cross 0, we infer that the effect is statistically significant. So similarly, I'll put the slides in the chat. We're going to go through these with mediation in R and SPSS. And here's the lines. We're going to breeze through the first parts, and you'll see there's not much to do in terms of syntax in SPSS for this. I'm going to go ahead and clear my environment, clear my console and everything, and go and open up my mediation file. Now, everything that we did in the moderation, lines 8 all the way through the missing data analysis and the descriptives, all the way through line let's see, where are we here? Right up to mediation. We can just run all of that again. Same stuff that we're doing, that we've done before. Going to generate our same table that we had before. I'm just going to exit it out, not let it do it. And for SPSS syntax, we're going to open up the mediation syntax and get rid of our moderation syntax. So this is a lot a bit simpler. See, we have nothing after the data that we've already done. All the cleaning we've already done. Our data set is, I believe it's still open, so I don't actually need to run anything in this syntax. But if you were starting fresh, you would want to do that. A lot of packages that we're going to be referencing or using, so install them or load the libraries to start. And in R, we're going to, again, mean center our variables. Flourishing, alcohol used in the past month, number of days, and the audit total. So our mediation model is going to look at alcohol use influencing, predicting depression through risky drinking behaviors through audit. So our first step here is just to check our multicollinearity, make sure that there's no variable inflation factors above 5. It's looking good. So if we do see suppression, which big clue, we will, we'll know that we already know that it's not an artifact of multicollinearity. So we've kind of already handled that by testing this. Lavon has some different syntax. You specify your model just as a string, right? So just in single or double quotes. And in Lavon, what we're doing is we're using these asterisks here to basically create labels for each of our paths. So here, you could just, model this. PHQ9 total is the outcome. Alcohol used in the past day means centered is the predictor for our direct path, our C. And if you put C direct and then an asterisk in front of this variable, you can now call it down below using a colon and equal sign. And so this is where you can start to run operations using the results to generate output that will show you the indirect effect, show you the direct effect, show you the total effect. So that's a little bit about what the syntax is. So we're specifying our C path separately from our B path, separately from our A path. This keeps things organized. The statistical conclusions will be the same if you included all three in this one and just included your A path separately. I like to keep it organized. So we're going to specify that model. And here we're going to run structural equation modeling, SEM. This is in the Lavon package. And we're going to say we want to use our model. We want to specify the data we're using, data. And for our standard errors, we want to use bootstrapping with 5,000 samples. Don't worry about these two lines. This is to help speed things up. I have 24 core CPU, so I'm parallelizing this. It's going to run a bootstrap sample on each of my 23 out of 24 CPUs, so it'll go a little bit faster, but we do want to set the seed so that our results are reproducible. This will make sure we have the same bootstrap samples each time. So I'm going to go ahead and run this. It's going to take some time to run all those 5,000, fit the model 5,000 times. You will see errors. Some of the bootstrap samples might not converge. As long as that is not a large proportion, like greater than 10 or 100 or 1,000, then you can kind of continue. But that's pretty normal. You're going to find some of them don't converge. So I'm going to go ahead and jump over to SPSS while this is running and put in our mediation model. As I said before, we want model 4 this time. Our outcome is our Y, our PHQ9. Our predictor is past month alcohol use, and our mediator is audit. We're going to change some, we're not visualizing interactions anymore. We are going to, we're not going to allow for this interaction, but we are going to show the total effects model, and we want to have some standardized effects. as well. We're going to mean center continuous variables, and we're going to choose, we want 95% confidence intervals, and we want to use 5,000 bootstrap samples. We want to select that we're using bootstrap inference for our model coefficients. This should already be checked, the long variable names. So we'll let this run as well. And while this is running, we're going to jump back over to R. So you'll notice that the results are going to be different between R and SPSS, and that's because the seed that SPSS process macro is using is the same every time, but they don't tell us what the seed is, so I just have to keep trying and guessing to try to make them identical. So the results will be slightly different. So here I'm going to extract from my fit the bootstrap results. I'm going to show all the coefficients, just a lot of coefficients, because you saw in the error, we had 2 of the samples fail to converge. So really this isn't 5,000 bootstrap samples, this is 4,998 bootstrap samples. If I turn these into a vector, show you the length, we have 25,000 bootstraps coefficients. I'm going to get rid of the NAs from those just so I can show you the distribution. This is why we don't trust p-values and we don't trust parametric tests of bootstrap samples, because this is not a normal distribution for our bootstrapped estimates. If I look at the QQ plot, you'll see it's certainly not normal. And I can even run a statistical test for normality and show that it's significant. Kolmogorov-Smirnov test for normality is significant, so we do not follow normal distribution. Just to show you, visually, this is why we're using non-parametric bootstraps. In Lavand, as I mentioned, the standardized solution is going to use that delta method, which we don't want to use. Some information here about it. So we're going to use this from SEM Helping Hands instead to get our standardized solution with non-parametric bootstrap confidence intervals. And then we're going to print that out. And you'll see our results here. Now we can interpret these for our indirect, direct, and total effect. Okay, looking at the time, we've got about 12 minutes left. So I'm going to go through jump back over to the SPSS output, and we'll walk through this. So first, what we have here is our A path. So audit total is the outcome. Outcall in the past month is the predictor. And we're seeing we have an R squared of 0.21, 21% of the variability in audit is explained by alcohol used in the past day. And for each increase in, for every additional day of drinking, audit is predicted to go up by 0.55. And this is a significant result. We can interpret our main effects, our p-values, but that's fine. But we can't interpret our indirect, direct total effects using p-values. The next one is the model predicting PHQ-9. So we're going to see both alcohol use and audit. We'll see that neither are significant. Both sets of confidence intervals cross 0, and the R squared is very low. So this is, the R squared for our total effect is only explaining, so alcohol the past month directly on PHQ-9 is not affecting, is not predicting, very much variability in depression scores, even with the inclusion of the mediator. Again, here's our total effect model, even less, right? So when we include that mediation, it's 0.004, so 0.04% of the variability. So this is not, this is, we go down to our indirect effects, we'll see that we have a significant indirect effect, but it's not very meaningful. Even though the indirect effect is significant, the total effect is not. So here's our bootstrap results. Actually, this is the one that we're going to be analyzing. Okay. So jump back over to R and talk a little bit about the suppression. So actually, I'm going to jump into our PowerPoint. So what we're seeing here is we have a suppression effect. How do we know? Well, we have opposite signs for our indirect effect and our direct effect. So indirect is positive, and our direct effect is negative. That's the first way that we know. The second way that we know is that the direct effect is actually stronger, more negative than the total effect. So what that means is that the inclusion of the mediator is actually suppressing the direct effect, or rather suppressing the total effect overall here. So when is it problematic to have this? If the direct effect is significant when there's no mediator and then becomes non-significant, like we see here, when we have the mediator, that could be a sign that it's problematic. Or if we have high multicollinearity, then it could be problematic. So we don't have multicollinearity, but we can test for this first one, significant change. So we'll do that down here. Just PHQ-9 being predicted by past month alcohol use. We look at our model fit. It's non-significant and very slightly negative. So it's not as though this is a significant effect without the mediator, but changing when we add the mediator. This is actually just non-significant overall. So that sort of suggesting that we don't have problematic suppression. Maybe there's a theoretical reason for that suppression. We already looked at the VIF, so we see we don't have multicollinearity. Then the last step here for testing problematic suppression, this is a big giveaway, is looking at the AIC IKICS, I believe, information criterion, which is just descriptively telling how well a model fits. Lower values are better. So we compare similarly our full model versus the direct effect model, and look at the AIC, and we'll see actually the full model does fit the data a bit better. It's pretty close, but it does fit a little bit better. So there might be a theoretical reason for this suppression, and we'll talk a little bit about that in the next few minutes. Don't use BIC for this test. This is going to penalize models that have more predictors. So it's going to give you if I run it, you'll see it shows that it would tell us that there's a substantial suppression effect that might be problematic, but the way it's calculated makes it not very reliable, especially in small sample sizes for this particular purpose. So looking at our results, I'm going to show the equations here as well as what we would, how we would show the figure. Again, we have significant A path, non-significant B and C prime paths. Direct effect and B path are non-significant, and our total effect is non-significant and very small. So could you publish this as a poster or get it submitted and approved as a poster or the manuscript? I mean, possibly if you had enough power. Is it really that valuable of a finding? That's for you to decide for yourself, and that's going to be based off the literature review and your interpretation of these results. So our indirect effect is here is saying, because it's standardized, our indirect effect of 0.104 is saying that for each 1 day increase in alcohol use, there is a predicted 0.104 increase in depression through increased audit scores. So if we were to go ahead and multiply this coefficient by 30, we would get the extreme values of this effect. If a student was drinking 0 days versus 30 days, what would be the difference in their predicted depression through this mediation path? Keep in mind, this is a unit in standard deviation change, not a single unit change for the indirect effect. So we'd have to look at the standard deviation, and looking at the time, we don't have time to do that. But given that this is a very low R squared for the full model on depression, and like you saw in SPSS, when you're looking at the R squared for the total effects model, it's even lower, substantially lower. This is not very meaningful But the suppression effect, as we sort of look at this would say, why would you think that alcohol use would predict slightly lower depression? Well, students are drinking more, right? There's more drinking days. They're probably socializing more. They're probably, maybe they have more friends, maybe they feel more connected to the folks around them. That would sort of explain these results here, the direct effect that we saw in our suppression fit, which is a very, very small decrease. And this is not the standardized results. So if I multiplied negative 0.0, what is it? 3072. If I multiplied this by 30, the most that the PHP-9 score could decrease through this direct path, is by 0.92 points on depression, without audit included. Now, when we put audit in, all of the risky drinking behavior, the variance from that is now included, right? So what we're going to be seeing here is, I'm realizing this should actually be a positive, 0.48. But what we're seeing here is audit is now sort of taken out of this connection. So what this is saying is that alcohol use, increased days of drinking, actually will decrease depression more when you take out the risky drinking components of alcohol use, right? So that might be a theoretically grounded explanation for why we have a suppression effect, is that maybe if you're drinking more days, but you're not engaged in any of the problematic behaviors, the risky drinking behaviors, then the days of drinking is actually capturing, perhaps an omitted variable, which is sense of connectedness or social support or something like that, number of friends, whatever it might be. That could be one potential explanation for this suppression effect that is actually really, could be fascinating if we had the right sample size and we had, a significant total effect. So that just as an example to show that depression can be kind of confusing. It can, your first, knee-jerk reactions should be, is this problematic? Is this just a statistical feature? But if you go through the steps and you find that it's not, this is one of those things that could be pretty interesting, meaningful, could guide future studies, guide you to sort of find other theoretically grounded variables to include in your model as a covariate, or maybe, like I said, as serial mediation or moderation. So, like as promised, we don't have time to go over power, in GPAR, but in the slides in the repo, I did include the link to download this. It's free, open source software you can use for power calculations. I'll pull it up just to show you what it looks like here. But it'll help you determine your sample size depending on the family of tests that you're using, the type of test, and the effect size that you want to find. And there is a formula for converting your R squared to F squared, so you can help to determine. In our case here, we would be needing to have a very sensitive, be able to detect a very small effect size because of how low this R squared is. That's it. We got 1 minute left in the time. Hopefully this was helpful. I know we went through a lot of this stuff really quickly, and didn't have much of a chance to go through the interpretation specifics for the mediation, but any hanging questions folks have, or extensions for this, more specific questions that I might be able to try to answer at least?
I don't have any questions, but I did want to say thank you. I think especially the mediation part, I forget what her name is, but the girl in the lab, Evan, that you did like a project with where you guys went through some of this data, and then she had the big mediation model thing, kind of like what's on this mediation result slide. I feel like I understand it now. So great. How to interpret that. So that's really helpful. So thank you.
Yeah, absolutely. Like I said, these videos will be uploaded for you to go through. And one of the things that, in my preparation of this seminar, it helped me to go through and refresh myself on all the nuances of this. And what I'll say is lean heavily into AI to help facilitate your learning on this, specifically cloud.ai, that's CLAUDE.ai, is a really good large language model that you can put your results in and just copy paste directly from R and put it in and say, help me understand, help me interpret these effects, tell it what the variables are, and it'll walk you through what each one is. You can ask follow-up questions. So if you're running some analysis, don't upload the data to a large language model. Definitely don't do that, but you can put your results in and what the variables are and ask nuanced questions about what it means and even talk about what was found in literature reviews that you've conducted and see what the model has to say about that to help ground and contextualize it. It is a great tool to help you start thinking about your findings in a really critical way. So lean into it for that. Also, if you're getting errors in R or in SPSS, lean into it for that too. Copy paste those errors into the AI and it'll help you troubleshoot some of that. So I do say, as I said to a number of folks, if you really want to learn this stuff and you want to go through it, there is nowadays between the YouTube tutorials and large language models, there's nothing that can stop you from becoming very, very well versed in this. So let's look at our power analysis. We didn't have time in the main seminar, so I'm going to go through the power analysis now. Starting with the moderation, our sample size was 81 in these analyses. And so let's ask the question, do we have enough statistical power? We're going to run through this using GPAR, which is free open source software for running power analysis. And the link is in the PowerPoints in the repository, linked in the video description. So you can, take a look at the link to download that, or just search in Google for GPAR, and you can find download links for free for Windows and for Mac. So for our moderation example, I put up our results here. Really our first test was looking at the ANOVA, comparing really R-squared change, right, where we found significant results here, that there was a significant improvement in model fit when we added this interaction term in the full model. So I'm going to treat this like it's a priori, even though this is after the fact, post hoc, to run this power analysis, just to get an idea of what sample size we should have had, given actually exactly what we found. So if I go over to F-test under test family, and I go to linear multiple regression, fixed model with R-squared increase, that's testing the nested models. What we're going to do here is we're going to determine our effect size, F squared, using our R-squared change. So what is the size of the R-squared change that we're looking for, that we actually found was 0.067. So if I calculate that, you'll see the effect size is 0.072, which corresponds to somewhere between a small and a medium effect size. So if I go to calculate and transfer, it'll transfer that effect size to the window. Again, this is the a priori method, so this is what you would do ahead of time. So you would want to determine your effect size based off what's in the literature, what was the R-squared changes that were found for this type of these types of variables of interest, and sort of estimate that. You can just use the small, in planning a study, you would just, based off literature review, say, well, I'm going to probably find a small improvement in R-squared, so you can just set that to the low one. That's generally what you'd want to do to be conservative, but we're looking at actual power here using the a priori method. So ideally you want to have a 1 minus beta to be 80% or higher. Beta being the probability of making a type 2 error that's missing a statistically significant finding, actually a real effect, but you're missing it. You're finding a p-value greater than 0.05. So that's what the beta is. So 1 minus beta, right, is going to be the likelihood, the probability that if there is a statistically significant finding at the p.05 level, significance level, cutoff, then you will have the sample size to detect that. So that's what power is. So here, 80% probability that if there is a statistically significant effect at the p, less than 0.05 cutoff, that there's an 80% chance that we're going to actually, our model is going to find that given our sample size that it gives us over here. So here, let's just say we're testing, we have a total of 3 predictors, and we'll make it, really conservative. We'll say that we want to test all 3 of the ones that we have. So that's going to be the predictor, and the moderator and the interaction term. This is going to give us the most conservative. And so what we actually found was this R-squared change of 6.71% of the variability in depression scores was the R-squared change when we added the moderator. So that's over here. We're going to use the conservative number of predictors and tested predictors and a p-value cutoff of 0.05. We calculate our sample size. Looks like we needed 156 participants to meet this sort of have adequate statistical power. And it'll show you the graph here in the critical F, that you would be going off of with that sample size. So if I were to switch this to post hoc, we put our effect size in here, and we put in our sample size. So we had 81 people. It'll give us our actual power. So even though we found statistically significant results, the likelihood that there was something that we missed, potentially at least one of the findings was missed, is 50-50. So we were underpowered in our analysis here if we run it post hoc. I'm going to go back to a priori and just show you here, if the effect size is very small, right, then you need a larger sample to be able to detect that. So if I were to keep all the settings the same and just calculate it with a small effect size, now we need 550 people. But if we wanted a medium effect size, we would only need 73 or 77 participants. And then for the large effect size, we would need 36 participants. The reason is, the effect is very large, then it should be present, given the law of large numbers, normal distribution, a large effect size should be visible 80% of the time when you have even a small sample size. Most studies suffer from being underpowered, but you can have too much statistical power, which renders your p-values kind of meaningless. That often occurs when you have an extremely large sample size, one that we could say actually resembles the population. So you're no longer testing a sample of the population. If you have 8, 10, 12, 20, 30, 40, 50,000 rows of data, that is looking more like the population itself. So you will, in that case, find that almost everything is statistically significant, even though your effects might be 0.0001. Incredibly small effects become statistically significant because you're measuring the population. So the likelihood that that's due to chance goes down. So less meaningful. So you might consider doing cross-validation or something like that, cutting down your sample size, using a smaller random sample of the larger sample size that you have to run your analysis so that you're not overpowered, so that you still have meaningful interpretations. And in that case, you would just set your effect size to small. You might be very conservative, say I want to, be confident up to the 0.001 p-value cutoff and have 95% power. And then if you calculate that, you can say, okay, I might have 10,000 participants, but let me take one randomly sample without replacement and create 2 1,500 participant samples from that 10,000. Then you would run your analysis on one of them, look at those results, and then cross-validate, run the analysis again on the other sample, and that will tell you if your findings are not significantly different. Then that's some of the most robust types of statistical results to report. Cross-validated results are incredibly powerful. In a sense, you're not only testing your model, but then you're validating it in a separate population that the model has not been fit on, already. So if the effects don't change between the first sample and the cross-validated sample, you're basically showing, yes, this effect exists and it is generalizable in this, likely to be generalizable in the sample population. So that is the moderation power analysis here. And then if we jump over to our mediation power analysis, we're going to go to our t-test and look at our linear multiple regression fixed model and look at our single regression coefficients. Similarly, we're going to do a priori, and let's just, for the sake of time, look at a small effect size, 80% power, and we know we have 2 predictors. So if we run that, we'll see in order to test the one-tailed t-test, finding a small effect size, which is what we were looking at actually in the total effects model. Our R squared was incredibly small. It's 0.0004, 0.04% of the variability in depression was explained through the total effect. And so if we calculate that and transfer it over, we see, wow, that's a tiny, tiny effect. So what would be the sample size with those 2 predictors we would need to actually be confident in and that we detected? Remember, we had non-significant total effects. So in order to be confident in that finding, we would have needed to have sample size close to a population, 15,451 people. But looking at the A path, so that was outcall in the past month predicting audit scores, we had a much higher R squared at 0.21. So if you calculate that and transfer it to the window, you'll see it's above, in between medium and large effect size. So calculating that, well, we can be really confident in that A path. That A path only required us to have 25 participants, and we had 81. And then our B path was a medium effect size, a little bit lower. We'll just run it at like 0.10. With the 2 predictors, we would probably need a bit more, so 64. Really, that was only 1 predictor, so we would probably even need fewer, about 64 is the same number of predictors. So that gives you an idea of how each of the tests that you have that you're running is going, each regression coefficient that you're looking at will have sort of a different power analysis that could accompany it depending on the effects you found. So again, if I ran through the post hoc for this and determined that total effect, right, which we had was 0.0004, incredibly small. Let's say we had 81 participants, 2 predictors. We can get our actual observed power. Oops, sorry, we have to transfer there you go. So now the effect size is what we actually found. We had 81 participants, 2 predictors. What was our actual power? Very, very low, severely underpowered. So that means that there is a 0.07, meaning that there's a 93% chance that one of our findings was statistically significant, but because we lacked the power, we missed it. We made a type 2 error. And so this is why power analyses are so important, because you can really make you're at high risk of making a type 2 error or type 1 error if you're underpowered. So hopefully that helps. This is just a very brief introduction to a power analysis for this example, but something, like I said, you can check out other videos to learn more about power analysis for your specific applications. So I hope this was helpful. And thanks again, everyone, for coming to the seminar today.